Hello and welcome back. In this video, we are going to talk about the properties of solutions, and they're called colligative properties. These are properties that depend on the amount of the interacting particles and not the type. So you have to keep that in mind. Once a solution is formed, we were not going to focus too much on what the particles are, the type of interactions, whether they're ion dipole or dipole or dispersion or any of that stuff. What we're going to look at, however, is the concentration, brackets means concentration, the concentration of the interacting particles within the solution. And I'll show you here a molecular representation so that you can understand what we're talking about. And the other thing that we are going to have to keep in mind is that these properties are compared to the pure solvent. Okay, so when we talk about boiling point or freezing point or whatever, it's always, the reference is always the pure solvent for those values. Now, let's take a look at the molecular behavior of solutes and solvents and solutions and the properties that will come from those. The properties that we need to think about are vapor pressure. Remember, this is the pressure of the gaseous molecules. It has to be in a closed container or a closed system, so let's close it off. And the number of gas molecules that are here that are colliding and exerting force, that is the vapor pressure. That's related, of course, to boiling point. We can talk about freezing point as well. We can always talk about enthalpy of vaporization and enthalpy of fusion and so on. However, those are all related. Once you understand the concepts for these, you can then think through the other properties that you may have to compare. All right, now let's say that we have, this is a pure solvent, and the smaller particles are a little bit farther away than where we're looking, and the larger ones are closer to us. And remember, in the liquid state, they're moving, there's a lot of motion. So as these molecules are just hanging out, moving and what have you, at the surface of the liquid, there are some molecules, let's say we have this one. This one might have been bombarded enough by its neighbors to have gotten to a high enough kinetic energy to break free and go into the vapor. Now we have one particle that has gone into the vapor. Of course, there are many more molecules than what I have represented. This is just for our discussion here. And another one goes out that's not drawn, and so forth. We end up having a certain number of molecules in the gaseous state now that are moving around and colliding with each other in the container, exerting force. However, they're also colliding with the surface. And some of them, as they collide, some of them are escaping, right? And as some of these collide with the surface, they may slow down enough from that collision to then get back into the liquid. And there's this dynamic process of the number of molecules leaving, going into the vapor, and those that are condensing. And it happens where there is equilibrium between those two processes. They're happening at the same rate. And at a particular temperature, the vapor pressure is going to be so much for a particular substance. And so since this is pure water, then it is, there are tables of vapor pressure of water at different temperatures. Vapor pressure, by the way, for pure substances is dependent solely on the temperature, will vary with temperature for a substance. Okay. What happens if now we have a solution? So this is our pure substance, right? And at the same temperature, we now have a solution. So we have all these molecules, the same types of molecules that we had before. But now we have some solute in here. Then remember, the solute dissolves because the solvent surrounds it, interacts with it, and then takes it into solution. So with these added interactions, there are less water molecules Actually, let me not say it that way. Let me say this. In order for this water molecule right here to escape and go into the vapor, and we'll make a closed system, unlike this molecule had to only overcome the hydrogen bonding with its neighboring water molecules. Here, look at this molecule. Now I'm going to color it in with yellow. I'll move out of the way so that you can see the yellow. This water molecule that's going to leave is going to require a lot more energy to break free than this one did because there are added interactions. It is being held or interacting with additional particles that are in solution, the solute. And so at the same temperature, if, let's say, the vapor pressure in this container is 25 torr, what's the vapor pressure going to be here? Here are your three choices. A, the vapor pressure is going to be less than 25 torr. B, vapor pressure will be 25 torr. Or C, I'm running out of room here, vapor pressure will be greater than 25 torr. Well, at the same temperature, same average kinetic energy, the molecule that we're focusing on, like the one that left here, this one has average kinetic energy same as this one. However, it has to overcome more forces. There's more force holding on to that molecule that it has to overcome. So at the same temperature, this molecule is not going to be able to free up and go into the gaseous state. So at this temperature, let's say we represented, I think I erased one of these, but 1, 2, 3, 4, 5, 6. If there are 6 molecules, relatively speaking, in this example, there may be only 3 or 4 or 5, depending on how much of the solute is present. We'll just show 5 here. Yeah, we'll show 5. So there are less number of molecules in the gaseous state, in the vapor above this liquid in the closed system. So the answer would be less than 25 torr. Okay, since boiling point, we'll come back over here. Since boiling point is the temperature at which the vapor pressure equals atmospheric pressure, the more particles that are interacting and holding on, the higher the temperature you have to achieve in order to reach, to have enough molecules going into the vapor to give rise to vapor pressure that's the same as the atmospheric pressure. So the more interactions, the lower the boiling point, right? And with more interactions, the lower the vapor pressure. Okay, now what about freezing point? Freezing point is an interesting one to think about because it's not intuitive right away. But let me explain something to you. When you are boiling, let's say you take a solution, salt water, okay, and you boil it. What exactly is boiling? What's evaporating? What's coming off? It's only the water molecules, because as it boils, if you leave it too long and it dries up, well, there's not going to be anything left in the pot. You will have something left, and that is the solute will remain behind. So when you have a solution, what you are boiling or freezing is the solvent only. So whatever you're doing, you have to overcome the intermolecular forces with the solute in order to freeze or to boil. So going to freezing, in order for the molecules now to overcome the intermolecular forces, you have to remove more energy to go lower in temperature in order for the solvent to freeze. Think about what we do on cold days, really cold days, and there's ice out on the roads. What do? We put out salt, because as the salt is put down on top of the ice, it interacts and starts dissolving and causes the water to go into the liquid state, and you form a saltwater solution versus a solid sheet of ice. Okay, and so at that temperature outside with some salt, you end up melting the ice. So you have to go, excuse me, hold on a minute. You decrease the freezing point and you increase the boiling point. You have to go to a higher temperature to achieve the same vapor pressure because the vapor pressure gets suppressed when you put in a solute. So excuse me for that. This is an increasing boiling point and a decrease in freezing point. Okay, and the interactions or the calculations, if you will, for these various things, we will not deal with the vapor pressure calculations or Raoult's law. We'll only deal with the boiling point and freezing point calculations. To determine the change in temperature, whether boiling or freezing, how much different the boiling point will have to be, how much higher in temperature you have to go beyond the pure solvent, or how much lower in freezing point you have to go beyond the pure solvent in order to have those phase changes for the solution. That's going to be proportional to the concentration of the interacting particles. I'll say particles. Okay, so how do we deal with concentration in changing temperature? Well, the only one that's temperature independent concentration unit is molality. And to get rid of the proportionality, we'll have a constant. This is called either the boiling point elevation constant or the freezing point depression constant, and it is for the solvent. The concentration now of the interacting particles is going to be the molality. Actually, let me write it this way. Moles of particles, interacting particles, per kilogram of solvent. Now let's take this apart. Well, molality is moles of solute, not the interacting particles, per kilogram solvent, right? How do we get to the moles of interacting particles? Well, for each mole of solute, you have a certain number of moles of interacting particles. This is called the Van 't Hoff factor, or I. So this comes then to the change in temperature is equal to K times the Van 't Hoff factor times the molality of the solution, of the solute, molality of the solution. Let me talk to you about I. For our purposes in this course, we are going to approximate to what I'm going to give you here. If you go back to the example that was given in a previous video, right? So sodium chloride, when it dissolves, you have 1 mole of sodium chloride. How many moles of particles that go out in solution and interact? There's a total of 2 moles. So for our purposes, for sodium chloride, I is going to be 2. So we double the molality when we plug into this equation and calculate the change in temperature. Okay, lastly, once you have done the calculation, and let's say that we have an aqueous solution and we find that the change in temperature for boiling is equal to 1.96 degrees. If this is water, that means the boiling point of solution, this is how many degrees above, right? An elevation of boiling point is going to be 101.96 degrees Celsius. So the boiling point for the solution will be the boiling point of the pure solvent plus the change in the boiling point. How many degrees above that the solution is going to go. For the freezing point, let's say that a freezing point, delta T for freezing of an aqueous, some other aqueous solution is 0.72 degrees. What is the freezing point for our solution then? Remember, the freezing point is lowered. So we start with 0 Celsius, that is the pure solvent, and it is going down, decreasing by 0.72 degrees Celsius. So the freezing point then is negative 0.72 degrees Celsius. That is the expected temperature that we would observe for that solution for freezing. And that, my dear students, wraps up our video on colligative properties.